Good afternoon. Today's lecture is on second order systems, and these have a transfer function of the following form: gs given by k omega n squared over s squared plus 2 zeta omega ns plus omega n squared. And in this transfer function, k would be the steady state k. More importantly, zeta, or omega n, should we say omega n, is the natural frequency, and zeta is the damping ratio. Now, for a second order system, the critical parameter is the damping ratio, and we have to consider three cases: damping ratio greater than 1, damping ratio equals 1, and damping ratio less than 1. And in the three cases now, if the damping ratio is bigger than 1, we call it heavily damped. And damping ratio equal to 1 is called critically damped. And when the damping ratio is less than 1, it's called lightly damped. And the transient response of the system, if we imagine now we have the system here, k omega n squared s squared plus 2 zeta omega n s is omega n squared. If we put a step in here, then we can get different types of transient response out here now. So the first one might be, say, when the damping ratio is bigger than 1. This will be the heavily damped case. And what will happen now is the response will be quite slow and won't show any overshoot. When the damping ratio is equal to 1, the transient response is faster, and is in fact as fast as it can be without making an overshoot. And then when the damping ratio is less than 1, the transient response is faster than this one, and now exhibits an oscillatory response. Now, the bulk of flight control systems, they fall into this category here: damping ratio less than 1 and an oscillatory response. And so what we concentrate on in second order systems is mostly on the critically damped, lightly damped case, and occasionally on the critically damped case. Now, associated with the lightly damped case, there are some equations that we have to know as well. I'm just going to put the equations down for you. So if we think of the, in fact, I'm going to put this over here. If we think the transient response might look something like this. We can now characterize the response shape by a number of key equations. The first one is the frequency of this response. This is called omega d, and omega d has an equation. Omega d is omega n into the square root of 1 minus zeta squared. That's the damped frequency, which is a little bit lower than the natural frequency. Next thing we have is this point here. It's called the peak overshoot. And the time, t star, at which the peak overshoot occurs, t star given by pi over omega d. And the last thing we might want to know is the size. The size of this overshoot here. And we can get that from the logarithmic decrement equation, which says that x2 over x1 is e to the minus zeta pi divided by the square root of 1 minus zeta squared. So here now we have got three key equations that is defining what's going on in this system here, and we'll use these then to do some analysis to work out omega d, t star, maximum overshoot, and those will be done in the coming up examples. Right, so back to our second order systems. Here's our standard transfer function for a second order system with a parameter zeta, omega n and k in. And so if we've got some transfer function, let's say it's given by g of s, it's given by, let's say, so 27 over s squared plus 4s plus 9. We could now, from doing a pattern matching calculation, we could work out what omega n, damping ratio and gain is. So the first thing we'll do is we'll say this 9 here is the same as this omega n squared here. So we get that 9 equals omega n squared, or omega n is 3 radians per second. So that's a nice quick way. Compare that one with that one. Next one is the 2 zeta omega n. And the 2 zeta omega n is equal to, in this particular case, 4. So we know now that omega n is 3. So 2 3s are 6. So zeta is 4 over 6, which is 0.666. So damping ratio in this particular case is 0.666. So it's less than 1, so it's lightly damped. And the last thing we know that k omega n squared, k omega n squared is equal to 27. Omega n squared is 9, so we get the k equals 3. Now in some situations it might be that we might have some number here like 2. So in that case these calculations wouldn't work. We have to have a 1 in front here. So if we did have a 2 there, we'd have to divide everything by 2. So it becomes 27 over 2, 4 over 2, 9 over 2. Now we got into this 1 in here, we could then apply the similar calculations, but this time clearly 9 over 2 would be omega n squared. So it wouldn't be quite such a nice number. But this is another key property now, that we can take our standard second order system equation, compare it with some numbers, and work out what the natural frequency and the damping ratio is. And that's our next thing that we need to know. So here's our first real example, and what we've got now is a little feedback control system, and we want to simplify this down to a single block and then compare it then with the standard second order system equations, so we could effectively work out for this system what the effective natural frequency and damping ratio and gain is. So let's have a go at doing that. So the first thing we do, follow the y around here. So that signal there is going to be v minus y, and then this one here, this will be that times that, so it'll be 9 v minus y. And we can say that this is that times that to get an equation. So y equals 9 v minus y over s plus 1. We can then move this term up here. So s plus 1 times 9 is 9v minus 9y. Expand this out, so get s squared plus s. We can bring the 9 over to give us a plus 9 times y equals 9v. And finally we can move this underneath to give us the y is 9v of s squared plus s plus 9. Now, having got into the standard form here, we can compare this with our standard equation. So we now know that omega n squared is 9. So we can say that omega n squared is 9, so omega n is 3 radians per second. We know that 2 zeta omega n this term here. So we know that 2 zeta omega n is 1. So zeta is 1 over 2 omega n. Omega n is 3, so that's 1 over 6, which is 0.1666. So damping ratio is 0.166, so it's quite lightly damped. And we also know this term here is k omega n squared. Omega n squared is 9, so therefore we could conclude in this particular case that k was 1. So that's taking a little block diagram like this, and then we can compute what omega n, damping ratio, and k is. Once you've worked out the natural frequency, damping ratio, and k, we can then predict what the transient response is going to look like. So we know it's going to look like something like this, and we know that k is 1, so this is going to go to 1. And we also know then we can work out some things now. We can work out what omega d is. So we do them here. Omega d, t star, and peak overshoot. So we can the expression now for omega d. So you know that omega d is omega n into the square root of 1 minus zeta squared. There's our standard equation for omega d. Then stick the numbers in now, so it's going to be 3 into the square root of 1 minus 0.166 squared. And if we work that out, we get omega d comes out as 2.95 radians per second. So omega d is always a little bit lower than omega n. Once you've got omega d, so we know that omega d is 2.95 radians per second. We can then go on to compute t star. So t star now is the time at which the peak overshoot occurs. So this is t star. And again, t star is given by pi over omega d, which is 3.142 over 2.95. And that one comes out as 1.06 seconds. So this is 1.06 seconds. And the last thing we could do is try and work out the size of this overshoot here, this peak overshoot. To work out the peak overshoot. And we have a little expression for that one as well. So we'll just write that one down and work it out. So the peak overshoot. So if we call this here x1 and this one here x2, then x2 over x1 is e to the minus zeta pi over the square root of 1 minus zeta squared. So it's a bit more complicated to work out this, but it's going to be e zeta, which is going to be 0.166 times pi over the square root of 1 minus 0.166 squared. So we'd have to compute that using a minus sign in there. We have to compute that using a calculator, and this one comes out as 0.585. So that means this, if this is 1, this will be 1.585. So that distance there is 0.585. So the peak overshoot, if this is going from 0 to 1, it would end up at 1.585. So it's got quite a big overshoot in this particular system. There's another thing we can do. So this is where we have all the numbers, and we can compute what the natural frequency and damping ratio is. There's another problem we can have where this is a gain now, Kp, and what we have to do then is choose a value of omega and damping ratio, and then select the value of Kp that gives us that parameter. So we'll look at that problem next. Right, so here's a slightly different problem this time. Closed loop feedback control system. This time we've got a gain in here, Kp, for proportional control, and a gain KD for derivative control, and we want to choose KP and KD, so it's the overall system has a natural frequency of 4 radians per second and a damping ratio of 0.5. So one of the things we do in this calculation is we put these numbers now into this expression here. So we're going to get s squared, 2 times zeta is 1, that's going to be 4s plus 16. So this is our desired second order system response we'd like, because if we had this one, then omega n would be 4 and the damping ratio would be 0.5. So we need now to choose Kp and Kd, because when we simplify this block diagram, the natural frequency is 4 and the damping ratio is 0.5. So we can do our calculation again. So this will be v minus y. This time this will be Kp plus s Kd into v minus y. Because this will be that times up, and then we can say that y is equal to 1 over s plus 1 into Kp plus skd v minus y. So this is that times out. Now rearrange this now to try and get into this form. So we can get s squared plus s times y is Kp plus skd times s plus Kp plus skd times y. That's a minus sign in there. Then what you can do is take these terms now onto this side. So you can get s squared plus, and I've got the 1s and kds. It's going to be 1 plus kd times s plus, and then we're going to have minus kp on that side becomes plus kp on this side. Kp times y equals kp plus s kd times v. If we move this underneath, then we finally get that y is equal to Kp plus skd times v over s squared plus 1 plus kds plus Kp. Now, we know now that this expression here has to be the same as this one here. So the expression s squared into 1 plus kds plus kp, this one has come from here, and this one now has to be the same as this one. So we can see now that this has to be the same as this, and this has to be the same as this. So kp is 16, so that becomes 16, and 1 plus kd is 4, so kd is 3. So what we have now is, let me put that the other way around. Yes, if we chose the controller now, 16 plus 3s in here, then this system would effectively have a natural frequency of 4 radians per second and a damping ratio of 0.5. And that's how we could then choose some controller gains to achieve certain natural frequencies and damping ratio in the closed loop system. And those are things you need to know about second order systems.
So here we have a little second order system, first order system here, integrator here, and we have a proportional controller and a derivative controller. The proportional controller set to 1 and the derivative controller set to 0. We can now run this as a simulation and look at the transient response. Click on the scope, so there's a transient response. It's got something like almost 20% overshoot occurring after about 3.5 seconds. As we increase the gain here, so we go for 2, the system will increase in its response time. Run it again. So we've just doubled the proportional gain, and you can see that's faster, a little bit more overshoot than last time, and it's faster, so it's speeded it up, but at the price of more overshoot. So we've got a faster response, but more overshoot. If we increase the gain again to 5, it's going to be faster again, but this time with even more overshoot. Let's have a look at this. This time we've got up to about almost 50% overshoot here. It is significantly faster at the start though. Now what we could do is now start to add in some derivative to bring this overshoot down. So if we put in a derivative gain now of 1, we can now run this, and this should have added in a bit of damping for us. So the derivative is now reduced, it's kept the speed, but it's reduced the overshoot. Similarly, if we put in 2 in here, we're going to keep the speed, but we're going to reduce the overshoot. Run it again. So this time we've got quite a small bit of overshoot here, about 5%. It's quite a good transient response, this one, and it's quite fast. It's tracking within about 1.5 seconds. If we overdo the derivative, so let's say we got a derivative of 5, then the derivative can slow it up too much. So if we run it this time, this is with too much derivative in. Now we find it's quite slow, hasn't got any overshoot in it. Significantly slower than last time. And if we were to take this to the extreme, let's say a very high derivative in, we could completely slow the system down. So now the system response is quite slow compared to the original response, which is up here somewhere. So we've slowed it down now by too much derivative. So choosing the correct proportional derivative in a feedback control system is one of the critical things we can have to obtain good closed system performance.